Okay, welcome everybody. My name is Josh Bongard. I'm a professor of computer science here at the University of Vermont, and I'm a member of the Proteus Institute. Proteus Institute is an institution, but currently residing at the University of Vermont, University of New Mexico, and Tufts University. And together, we are trying to understand how biological systems adapt and grapple with the world around them. And we're trying to learn how to create AI that can distill out adaptive potential from organisms and imprint those adaptive strategies into robots. So the main goal of the Proteus Institute is to try and steal ideas from biology to make better robots, robots that can adapt and continue on with whatever we want them to do as the world around them changes. Okay. So a little bit about the Proteus Institute. I'll just drop the URL for the Institute into chat. And again, I'm Josh Bongard. This is ProteusTV, and today I'm streaming episode 1 of season 2 of ProteusTV. We have all of the episodes from season 1 available on the About tab on our Twitch channel here. We stream every other Friday. There will be another member of the Proteus Institute here 2 weeks from now at 3 o'clock Eastern Time. Okay, what we're going to do in my stream today is I'm going to walk you through coding up a virtual robot, like the virtual robot you see in the bottom right of the stream, and we're going to code up that virtual robot in a virtual world, and that virtual world and virtual robot are going to be simulated by a physics engine. We're going to be using a particular physics engine today called PyBullet. Okay, at any time, please feel free to stop me and ask chat. We just had some issues with the audio. Hopefully everyone can hear me okay now. Can someone who's here on the stream just type into chat that they can hear me okay? Okay, you can hear. Great. All right. Okay, so let's dive right in. I mentioned we're going to be using the PyBullet physics engine. So for those of you that are on a Mac or a PC, you can pip install PyBullet. I already have it installed, so the requirement is already satisfied. Okay, no problem. Basically, what I'm going to be doing today is following some programming projects that you can follow along as well. And those programming projects are available at my MOOC. Which you can find at reddit.com/r/ludobots. So you can either try and follow along in real time with me today, or watch the stream, and then after the stream, head over to the Ludobot subreddit and give this a try yourself. Okay. Okay, so let's start by creating a simulation, or simulating a virtual world. So I'm creating a file called simulate.py. And first thing I need to do is import the particular physics engine we're going to be using, which is PyBullet. And I'm just getting a message back saying that I was able to successfully import PyBullet, so that's great. Okay. Next thing is I'm going to create a physics client. This is an object hierarchy that houses a lot of the physics. I'm going to connect to it. And I'm going to pass in an argument indicating that I want to use PyBullet's graphical user interface, or GUI. Whatever physics is being simulated, I want that to be shown on the screen. Okay. All of the magic is going to happen here, which we'll talk about in a minute or two. When we're done simulating our virtual world, we disconnect from the physics engine, from the physics client. Okay. You'll notice when I run simulate.py now, for a very brief instant in time, there's a graphics window that opens, but because I haven't asked PyBullet to simulate any physics, it immediately closes again. So let's get it to do some interesting stuff. Okay. We can simulate different kinds of virtual worlds in PyBullet. Let's simulate an environment right here on Earth by setting the gravity to Earth normal, minus 9.8 meters per second squared. We're going to simulate a robot like you see on the bottom right of the stream that's moving along on flat ground. And we're now going to create a for loop that's going to iterate from 0 to 999. And for now, we're not going to do anything more than just print the current time step and end. The reason we're creating this for loop is that in any physics engine, you set some aspects of the state of the system at a given point in time. At that point in time, the physics engine looks at each of the virtual objects inside your virtual world and computes the forces that are acting on those objects. At the moment, the only force that's going to act on objects is the force of gravity that is going to try and pull objects down. So whatever the current position is of the objects in the world at a given time step, at the next time step, the next time we iterate through this loop, the positions of the objects are going to be a little bit lower. And you'll see that in action in a moment. Okay. If we run our code now, you'll notice that my MacBook Pro very quickly iterates from 0 to 999. Okay. Now we are going to tell PyBullet to step through the simulation. So it's going to do one time step, and it's going to update the state or the positions of all the objects at this point in time. So stepping the simulation means moving from one time instant to the next. Again, things go very quickly, so quickly that we can't even see our virtual world. So let's slow things down a little bit. We're going to sleep this code for a 60th of a second at the end of each time step. So each time step in the real world here is going to last for 1/60th of a second. And I need the time package to do so. Okay. So when I run my code now, you can see that the numbers are running up to 999 a little bit slower. And if I now move my mouse, you can see that I am operating a virtual camera that is looking inside of a virtual world, and that virtual camera is pointing at 0, 0, 0, the origin or the origin point in this virtual world. So 0, 0, 0 is right here. Okay, so I now have an empty simulation. Okay, so far so good. Okay, so now we need to tell the physics engine to simulate something. So I'm going to create a second program called generate.py. And this file, generate.py, as the name implies, is going to generate some virtual objects for our virtual world to simulate. Okay. Let's put an empty statement in here for now, which doesn't do anything. Okay, so what is generate.py actually going to generate? It's going to generate, we're going to send a bunch of objects, but those objects taken together are going to represent a robot. Okay, so let's create a robot class, which is robot in capitals here. We're going to create a robot, and then we're going to save that robot to a file. So we've got two programs at the moment, generate.py and simulate.py. Generate.py is going to save out a file that specifies a virtual robot. And simulate.py, when it starts up, it's going to read in that virtual robot from that file and simulate that virtual robot inside the virtual world. Okay. So first of all, we need to define exactly what this virtual robot looks like. So let's start doing that. Okay, so we're creating a class called robot. Create a constructor. Which doesn't do anything at the moment. We have generate, which is going to create a robot. If we run generate, it's going to give us an error because our class does not have a save method associated with it. Okay, we run generate, and it doesn't obviously save out any file because there's no robot yet. Okay. So as you can see in the video, on the bottom right, we're going to make a snake robot, and if you squint carefully at that looping GIF, you'll notice that the robot is made up of 20 parts. So we're going to build up those 20 parts. Those parts are known as links, which is a little confusing. I want you to think not as links of things that link things together, but links as in sausage links. So we've got 20 links there that make up the snake. Between each pair of links, there is a joint, not unlike your elbow joint or your knee joint or your shoulder joint. A joint connects neighboring pairs of links together. So we're going to make a snake that's made up of 20 links and 19 joints. So the first joint is going to connect the first link to the second link. The second joint is going to connect the second link to the third link, and so on. Okay. For those that are joining, I'm coding up the virtual robot that you see bottom right. Feel free to ask any questions about what I'm doing, who I am, what the Proteus Institute is. Ask anything at all. I'm happy to do my best to try and answer it. Okay, so let's go back to our robot class. And let's define, let's set number of links in our snake. Eventually it's going to be 20, but let's start with just one for the moment. Let's create a function called createLinks, which is actually going to create each of these pieces or links that make up our snake. At the moment, this function doesn't do anything. Okay, so we're generating nothing yet. Okay, so let's get on to the fun part. We're only creating one link at the moment, so let's just call this function createLink. Okay, we're going to use a new package now called PyroSim, and I've already installed this package or downloaded this package. I will put the link in chat here for those that are interested in PyroSim. Okay, you can go find that package there. As I mentioned, I'm coding up something from the Ludobots subreddit, the Ludobots MOOC, and you can go to the MOOC and there's instructions for how to find PyroSim and install it. PyroSim is short for a Python robot simulator, and PyroSim is a wrapper. It's going to wrap around PyBullet. PyBullet has a pretty steep learning curve. There's quite a bit to learn how to get started and make robots, make virtual robots using PyBullet. PyroSim makes your life a lot easier. So we're going to use some of PyroSim here. The first thing we're going to do is we're going to send a particular link, and as you can see, the links or the parts of the snakes are a series of cubes. So we're going to send a cube. Sorry, I got this wrong. Okay. We're going to, when we save out our file, we're going to save out just one cube. So we're going to save out PyroSim send cube. We're saving out our virtual robot to a file. So we're just going to skip over creating the links for the moment and just get straight to the fun stuff. And then we'll circle back. Okay. You'll notice that send cube, when we send a cube, we need to give PyBullet some information about this particular object. It needs to have a name, it needs to have a three-dimensional position in space, and we need to also give it a size. So in createLink here, we're going to have to set the name to something. The position is going to have to be in XYZ coordinates. And the size, we're going to make each cube 1 by 1 by 1 meters, centimeters, millimeters. In the virtual world, we don't have any absolute distances, so you can just think of these as arbitrary distance units. So we're making a 1 by 1 by 1 cube. We're going to give this link a very uninteresting name. Just going to call it 0. In computer science, we always start counting from 0. We're going to make 20 different links or 20 different parts that make up the snake. Link 0, link 1, link 2, and so on up to link 19. Last thing we need to do is figure out what the position of this cube should be. Let's start by putting the cube, as I mentioned, at the origin, at 0, 0, 0. Okay, So when we create a new robot, it's going to create a robot that's made up of just a single link. That link has a name 0. We're going to place it at the origin, and the link is going to be a cube that is length 1, width 1, and height 1. Okay, so let's go back to robot for a moment. We're saving out just a we're going to save out just a single cube, but we need to tell PyroSim what file to save this information into. So we're going to wrap around this file another command, start.urdf. It's a little cryptic. URDF is a common file format used in robotics. So if you open up a URDF file, there's usually enough information there that describes the body of the robot, how all the pieces fit together, sensors and motors, all the things you'd expect on a robot. Okay, so we're going to open that file and we're going to save out the robot's body into this particular file, body.urdf. We're sending into that file information about just a single part. So for the moment, our robot is made up of a single cube. And when we're done, we end, which cleans up the file, and off we go. Okay. So let's review what we've done. We're creating this generate.py file that creates a robot and then saves it out to a file. We go back to robot.py. Here we go, creating it, and then when we save it, it's going to be written into this file. So let's run generate now, and we get an error. I have not included PyroSim. I've not imported PyroSim. Okay. So I now have a file written out called body.urdf, which should include all of this information. So if I open body.urdf, here's all the information inside that file. As you can see, it's pretty complicated. So this is just a visual reminder for why we're using PyroSim. PyroSim hides a lot of the dirty details that PyBullet requires. Okay. We run simulate again. We don't see our robot yet because we haven't told PyBullet to read in that particular robot, which we will do now. So now we're switching back to simulate.py. Here we're setting up our virtual world, simulating our virtual world, and then closing down our virtual world. Okay. So just before we start the physics, just before we enter the for loop, we're going to use PyBullet, and we're going to tell PyBullet to read in a URDF file. And remember, a URDF file encodes a robot. And we tell it which particular file we're interested in. And that should be it. Okay, there's our single part of our robot, and we notice that it's falling through the floor and downward forever. Okay, so we got we're missing some pieces of our virtual world. What are we missing? First thing we're missing is a floor altogether. You'll notice this wireframe picture is just showing you actually height of z equals 0, but there's no actual floor. So remember that we do have gravity in this world, so gravity is tugging downward on our single object, and because there's no floor, it will just keep falling forever. So let's add a floor. Okay, so in the same way that we just created a robot, let's create some other objects. We're going to make a special object here known as the plane or the floor. This comes preloaded with PyBullet. We don't have to define this ourselves. Okay, there's another little piece of information. I need to tell PyBullet where to find this URDF file. So it should be able to find the floor now and then simulate it. Did not. What am I missing? Okay. I'm using a different library here, pybullet_data, so I need to import that as well. Okay, we've got our floor now, but we see something is still not quite right. We'll notice that the single object making up our snake robot so far starts at 0, 0, 0, and then goes flying up into the air, and then gradually falls back down and settles on the ground again. Okay. So what's going on? I will try and pause the simulator here. Actually, let's just slow things down. That's probably easier. Okay. Now our simulation is going to run much slower. You'll notice that the block goes flying upwards out of the ground. At the beginning of the simulation, the object is placed inside the plane. The plane is at a height of z equals 0, and the position of our single object here is x equals 0, y equals 0, z equals 0. One of the things that the physics engine does for you is detect if any pair of objects are interpenetrating, if the surfaces have pushed past one another. Generally speaking, in the real world, that's impossible. So the PyBullet will try and make the physics more realistic in your world by applying forces to push interpenetrating objects further apart. So this single object is interpenetrating with the floor. So at the first time step, as I mentioned, at every time step in the simulation, PyBullet is stepping the simulation for us. At each step, it's looking at each object and applying forces relevant to that object. One force that all objects get is gravity, pulling them down. Any objects that are in collision or interpenetrating with any other objects, additional forces are added to them in the direction away from the object they're interpenetrating. So it's applying forces to pull those objects apart. Okay. Let's actually speed things up a little bit. Okay, so to see this process at work here. So let's help PyBullet a little bit. Instead of placing the initial position of the cube in the floor, let's put the object just above the floor. Okay, so we need to go back to robot.py. Inside robot, we're creating a single link. Remember, link is the name for objects in PyBullet. And we set the position to be x equals 0, y equals 0, z equals 0. Z is the vertical axis in PyBullet, so we're going to place the object at 0.5 units above the ground. The height of the object is 1, so if we place the center of the object 0.5 units above the ground, the object should start directly on the ground. And I actually made a little cartoon of this to make this a little bit easier to see. So here's our cube here. We're looking at it from the side. Whenever we give the position of an object, we're actually defining the position of the object, the position of the object's center. So we're setting the position to be 0, 0.5. I can't draw very well in 3D, so I've thrown away the y coordinate, and we're only going to use the x and z coordinate to build up our snake. Okay, so we're placing the object's initial position at x equals 0, y equals 0, and z equals 0.5 now. And it should start resting just on the ground. Oops. I ran simulate, but I forgot to regenerate the robot. Got to run generate first to generate this new robot, and then simulate it. And there we go. Okay, it starts sitting on the ground. We can convince ourselves that it's actually a physical object. I'm going to slow things down. We can convince ourselves that this is actually a physical object. One of the nice things about the PyBullet physics engine is it's very interactive. So with my mouse, I can grab the object and move it around, and you'll notice that it does not interpenetrate with the ground. Anytime it comes near to the ground, there is a force pushing the object upwards, which keeps it from passing through the ground. Okay, so far so good. Okay, I'm going to refactor my code a little bit. Our robot is going to be made up of more than one link, so we're now going to add two links. So I'm going to redefine this as create links. And I'm going to create inside a robot a dictionary of links. So every entry in the dictionary is going to correspond to a different link. And I'm going to iterate for link in range. I'm going to iterate over the number of links that we want our snake to have, which is now going to be 2. This is the link index. Okay, so we're going to create a new entry in the dictionary, and we're going to do so by calling the constructor of a new class that we're about to create called link. And we're going to move this code in there. Okay. So we're going to import this new class called link, and we're then going to go and create it. For the moment, we're going to assume it doesn't do anything. And take all of these nitty-gritty internal details about links and take it out of robot and put it into link. Okay, we can get rid of them from here. Okay. This specific line here, pyrosim, again, this is sending information about a particular link that has the shape of a cube. So we're going to hide this in the link link class as well. So we're going to iterate over all the links. And we're going to save each one out to the file. Okay, so we're iterating over each link, and we're going to save each link into body.urdf. Okay, we need to import pyrosim. Don't need it in robot anymore. Okay, so we're creating, whenever we call this link, we're just creating a link at this particular position, this particular size, and then when we save it, we're saving it out to the file. Okay, just to make sure everything works, let's just back up a moment. Let's just create a single link, and then call create links to generate it, generate each one. And let's just make sure we pushed everything correctly into the link class. This is just a little bit of refactoring. We still need that in robot.py. We still need pyrosim in robot.py. Okay. Please feel free to stop and ask any questions at any time if you like. Okay, generate. We've written out, whenever we run generate, we're writing some information into body.urdf. And here is all the information about the single link that we are sending to PyVolate. Let's simulate it to make sure everything's still fine. Okay. Okay, we're all good. Okay, so now we can, it makes it a little bit more easy to change the body of our robot. We can change it to number of links equals 2. We're going to call the link constructor twice, and every time it's going to create. We're going to call it twice. We're going to create 2 links. We're going to create 2 links with the exact same name, the exact same position, and the exact same size. So that doesn't make sense. We want to make sure that every link has its own name. So we're going to pass in link name. So we'll just call this name. And then we need to go back to robot.py, which is where the links are created. And the name of the link is simply going to be a string of the link index. And then we pass that in, link name. Okay. So now when we run generate, we should be writing into body.urdf two different links, one with the name 0, the other one with the name 1. And if we look inside here, we can see here's the first link with link name 0, and here's the second link with link name 1. Okay. They still have the exact same position, so we're putting two cubes at exactly the same place, but let's see how PyBullet deals with that. When we simulate these two links, we get an error. Okay, so what's the problem? I'm not going to describe the particular information there. The problem is that when we're making up a robot, it can't be made up of a disconnected series of objects in the same way that you are not made up of a disconnected number of bones. All of your bones have to be connected together into one body. So we need to do the same thing. We need to take our two cubes and attach them together, and we're going to attach them together with joints. So just to bring up a cartoon picture again for a moment, we just made one link. We've made a second link here called link 1, and we're going to place at the point of intersection of these two cubes, we're going to put a joint, and that joint is going to have a very uninteresting name, 0_1. The name indicates what this joint does. It connects link 0 to link 1. So let's enrich our robot class a little bit to allow for the creation of links and joints. So we're going to create a new class called joint, which describes how to connect pairs of links together. Okay, so we've got an empty class for the moment. It doesn't do anything. Remember that I said that whenever we create n links, like the 20 links that make up the snake that you see, we always need to create n-1 joints. So 19 joints in the snake that you see in the repeating GIF there. If we have n, we're always connecting neighboring pairs together, so we always have one less joint than we have links. First thing we do in robot.py is create links. Next thing we do is create joints. So in the same way that we created inside robot.py a dictionary of links, we're going to create a dictionary of joints. Okay, so we're following the basic flow here of create links as we create joints. We need a for loop here that's going to iterate over joint index. And before we need to count, we need to create one less joint than links. Okay. We need to create a joint name, which, as you saw before, is 0_1. When we're connecting object 0 to when we're connecting link 0 to link 1. So we can do that as following. Okay, so that's the name we want. So we're going to do that by stringifying joint index. First time through this loop, joint index is 0. We want to keep the underscore, and we're going to stringify joint index +1. Okay, that should create one joint called 0_1, and create links should create two links. The first link called 0 and the second link called 1. Let's just make sure that that's what happens when we run generate.py. Okay, there we go. So there's the creation of link 0, the creation of link 1, and the creation of the single joint 0_1. Okay, at least we got the names right. So like we did down here for create links, we're going to store our new joint in here, and we're going to call the joint constructor. We're going to give it the joint name. There's a little bit more information that we need to provide for any joint that we create. The first piece of information we need to give is what are the names of the two links that it's attaching together, and we also need to give our joint a position. Okay. So you can see the position is 0.5, x equals 0.5, and z equals 0.5, because the joint is at x equals 0.5, z equals 0.5. We're going to set the joint to sit right where the two cubes touch one another. Okay, so we've just created the joint name, the joint position, as we just said. Sorry, we need to give some more information. We need to give the name of the parent and the name of the child. So remember that we're connecting 0 to 1. We're going to use this notation parent and child. So parent is kind of the bone, if you like, that's upstream, and child is the bone downstream that's going to connect to the upstream bone. Yeah. So the 0 bone is connected to the 1 bone. That's basically what we're telling PyBullet about this particular joint. Okay. So we can use basically what we just had up here to do that. Okay. So first time through this for loop, we're going to create a joint called 0, 1, which is going to connect link 0 to link 1. We create a second joint. Joint index is going to equal 1. We're going to call that joint 1_2, and it's going to connect link 1 to link 2, and so on. I mentioned we need to give a position as well. For now, we're just going to set the position of that joint to be at x equals 0.5. We're not using the y. We're not using the y coordinate at the moment. We're only building in 2D, even though we're building inside a 3D virtual environment. Position is x equals 0.5, y equals 0, and z equals 0.5. Okay. That's pretty much all the information we need. We have the joint's name, parent, child, and position. Let's pass that information into joint. Name, parent, child, and position. Okay. So we have 4 arguments that we're passing into the constructor for joint. Name, parent, child, and position. Just going to store this information inside the object instance we make for now. Okay. Got all that information stored. So let's go back and remind ourselves of what we're doing. We're creating a bunch of links and then creating a bunch of joints. Okay. We've done that here in create joints, create links. And in robot.save, we're opening a URDF file. We're dumping or saving all of the links into that file. We're now going to also dump in all of the joints. Actually, I'm sorry, I can make this a little bit easier on us. Okay, so we're going to save out each joint to body.urdf. Okay, so let's have a look at link for a moment. Here's the save for link. We're sending a cube to the file. So in joint, we're going to do something similar. Okay, we're going to make use of pyrosym again here, which means I need it at the top. Okay, so I've imported pyrosym. Instead of sending a cube this time, we're going to send a joint, and we need to, as you can imagine, save into the file the name of the joint, the parent or upstream bone or link that the joint is connecting to, and the downstream bone or joint that the joint is connecting to. So the joint is going to connect the child back to the parent. I'm going to give a little bit more information here. Hopefully you can still see this okay. We need to tell it what type of joint to make. Revolute just means like a rotational joint, revolving joint, which is very much like your knee joint or your elbow joint. And the last thing we need to provide is the position. Okay, it's a pretty long call, but you get the basic idea. Okay. Okay, so now if we run generate to generate our robot, we're going to still get an error. Okay, make sure I'm importing pyrosym correctly. Okay, no errors. So let's have a look and see what's inside body.urdf now. Okay, there's the first link, link 0. Here's link 1, the second link. And we've got a single joint being stored in here that connects link 0 to link 1. Again, as you can see, we're using pyrosym because it hides a lot of the dirty details that PyBullet requires. Okay, so now after all of that, we should be able to simulate our creature. And we've got a little bit of an issue already. We can see that the two objects started as interpenetrated. So something is wrong. But if I grab and play with one of these objects, you'll see that the second object or the second cube comes along with it. So we've at least got one thing right, which we've managed to connect. Managed to connect the two links together. So what's the problem? The problem is the way we've specified the positions of the links and the joints. I'm not going to talk at you too much, but just to explain a little bit about how this works. PyBullet mixes absolute and relative coordinate systems. What does that mean? So absolute coordinate system means the coordinates, any of the positions, are absolute. So they're not relative to anything else. When we create the first link, it has an absolute coordinate. When we create the first joint, which we just did 0, 1, it also has an absolute coordinate. It's set at x equals 0, z equals, x equals 0.5 and z equals 0.5. When we add a second link and connect it to an upstream link, link 0 here, we're going to actually specify the position of this link with a relative coordinate, and it's going to be coordinates that are relative to its upstream joint. So if you think about your skeleton as a tree, where your torso is the root and your finger bones are the leaves, you can imagine things flowing upstream from your fingers to your center, to your torso. And you can also think of stuff flowing downward, downstream to your fingers and toes. So we're going to talk about upstream and downstream. So any link that has an upstream joint that connects it to an upstream link, we're going to give it a position that's relative to its link. Okay, so if we want to place our object here, we're placing it x equals 0.5 to the right of the upstream joint, x 0.5, and the z is 0. So we're taking one step to the right and no steps up or down. So we're telling it that link 1 is x equals 0.5, z equals 0, relative, its position is, that's its position relative to the upstream joint. Why do we do that? The reason why we do that is if we wanted to create a swarm of snakes, all we need to do is write out 100 different URDF files. Each of those 100 URDF files is going to contain a different snake. We're going to simulate 100 snakes, and each snake is going to be specified in each of those 100 URDF files. We're going to start by putting those 100 snakes at different positions. The only thing we need to change across those 100 positions is the absolute coordinate of the first link and the first joint. Everything else about the snake is relative to the head of the snake, if you like. Right? Makes things much easier to generate a swarm of robots. Okay. Obviously, you're just watching the stream. You don't need to remember all these details about absolute and relative coordinates. I just thought I'd explain that for those that are interested in the nitty-gritty details of physics engines. Okay, so we need to fix the position of our second joint. It should be 0.50. Okay, so at the moment, whenever we create a link, we're always placing it at the same position. That doesn't make sense. So we're going to have to parameterize this. We're going to pass in the position for every link that we create. So we've added a second argument here to our constructor. We need to go back to robot where we actually create the links, which is in here. So we're iterating over this loop. Twice. The first time we're placing something at 0.5, and the second one we're placing at 0.50. As I just mentioned, there's a difference in the way that we create the first joint and subsequent joints. So I'm just going to make this a little bit easier by commenting this out for a moment. And I'm going to manually create two different links. I'm going to create one here, and I'm going to create a different one here. Okay. Each of them require us to call the constructor down here. Okay. The first one, the link name is 0, and the next one is 1. And we need to send a position now. We need to send an XYZ for the first one and an XYZ for the second link. These need to be absolute coordinates. These need to be relative coordinates. I'm cheating here, and I'm just going to use my information here. So link 0 is at 0, x equals 0, y equals 0. We're not using y at the moment, and z equals 0.5. Okay. Second link is being placed. At x equals 0.5, y equals 0, z equals 0. Plug that in. We'll get back to this for loop next time. We only have 3 minutes left, so I want to see if we can get this to work. Okay. And we're just double checking our single joint that we're creating here is placed at 0.5, 0.5. That's this joint here. X equals 0.5, y equals 0, z equals 0.5. Generate, we're going to check body.urdf again. We've got a single link in there. Second link in there. And a single joint. Okay, let's see if we got everything in the right place. Okay, if I shake this a little bit, you should be able to see that we have our two objects connected. And they are connected by a joint at exactly where they overlap. There we go. Okay. Okay. So far, so good. I think this is a good place to pause for today. So again, my name is Josh Bongard. I'm a member of the Proteus Institute. We're dedicated to learning as much as we can from biology and teaching AIs how to channel that biology into more adaptive robots. Today I was showing you a bit of the nuts and bolts about how we do things, which is usually we start by simulating robots in virtual worlds before we tackle trying to build them in reality. Please tune in for episode 2 of season 2, which will be held in 2 weeks from now at 3 p.m. Eastern Time. For those that are tuning in live Friday afternoon, have a good rest of your day and have a great weekend. Thanks, everyone. Bye-bye now.